So please join me in welcoming Ibrahim for his lecture tonight.
Thank you everyone for coming today. I'm very excited to see a lot of people here. I am hoping today to describe to you, first of all, what a neutrino is, why it's important to do astronomy with neutrinos, and why it makes total sense to go to Antarctica and dig a 3-kilometer billion ton hole in the geographic South Pole to do that. So I hope I can succeed. So today's talk will start with an introduction on what a neutrino is, and then, like I said, I'll move to why we do neutrino astronomy, and then I'll motivate why we need to go to Antarctica, and then finally I will show you a little bit of what building this detector has given us in terms of science output and what we can hope for in the near future. So in the late 1800s, Marie Curie was deciding on a thesis topic, and given that a woman was not awarded a PhD before her in France, she needed to find a good one. And she decided to work on something that had just recently been discovered, radioactivity. In fact, she helped discover radioactivity and got the Nobel Prize and her PhD in the same year. And so what we discovered from her work was that neutrons can turn into protons and vice versa. So the nucleus is unstable, and there are some nuclei that are more unstable than others. And nature likes, for some reason, that the number of protons and neutrons in a nucleus are equal. And so when that's not true, there's a process that can happen by which it evens itself out. When she did that, another pioneer in nuclear physics, Lise Meitner, was, on top of being a pioneer in nuclear physics, was a skilled photographer. And she was using methods of photography to try and measure the radiation that's coming out of these nuclei. And she discovered something very interesting, that the energy that's coming out of the nuclei is not what we expect. It's less than the energy that should come out of the nuclei. And so that was a topic of debate for many, many years, for 2 decades actually. And one hypothesis was that energy is not conserved. And then we're truly in trouble here, because that's what we base most of our theories on, energy conservation. But there was another possibility, and that was posed by Wolfgang Pauli, an Italian scientist, in 1930. He was supposed to attend a conference that Lise Meitner was hosting. He couldn't go, but he sent a letter and he said, I've been thinking about this, and either energy is not conserved or there's something else that's coming out of the nucleus that takes the rest of that energy. And then because we can't detect it, we don't see that missing energy, but it adds up in the end. So he was right about that. The missing energy was being carried by the neutrino, which we now know exists. What he was not right about was predicting that it will never be detected, because it was such an elusive particle that was very hard to detect. In fact, Pauli was notoriously a very bad experimentalist. He was a great theorist, but there were stories about him actually breaking experiments just by being in a building, in the same building as the experiment. He's a very fascinating man, if you can look him up, and he has some correspondence with Carl Jung about mysticism. And in any case, the neutrino was detected. The neutrino was detected only 20 years later by Cohen and Rines at Los Alamos. They had two ideas. The first one was to detonate a nuclear bomb, and at the same time, because the shock wave from the nuclear bomb will really ruin any detector that you have next to it, to build a vacuum tank and then drop the detector in vacuum suspended while the nuclear bomb is being detonated. Because shock waves only travel in air, that way it will not affect your detector, and then you'll catch some neutrinos. And that project was in fact approved, and construction began. The Department of Defense was very keen on detecting the neutrino. But then one of their colleagues at a workshop had a good idea, and they suggested to use a nuclear reactor instead, and they had a good idea of how to remove the background. So they went with that instead of this. But they detected the neutrino in 1956, and this is the main experimenters. So this is Rhines, and this is Cohen. And this is their small tank that they put next to a nuclear reactor and just caught some neutrinos that would, in the same way that when a beta decay happens, you emit a neutrino, you can reverse this process and you can catch neutrinos when they interact with nuclei. Okay. So since then, we've learned quite a bit about these particles, and I'm going to step back just for a second here and try to put this together with everything else we know about particle physics. So we have an equation that describes how every particle interacts with every other particle, and it's very successful. It's called the Standard Model. It's very precise, and it's predicted many, many things accurately. And so that is a hallmark of a good theory, is when it can predict many things and it can do it accurately. But when you try to fit neutrinos in there, it just doesn't work. They predict that neutrinos should be massless, but we've discovered that neutrinos have mass experimentally, and that is a prediction that the Standard Model got wrong. Now, to maybe illustrate why this is very exciting to someone that works on particle physics, I will use an example of a rubber band. So if I have a rubber band and I want to write down a model that describes how this rubber band works, I can say, I can play with it, and I can find out that when I exert a force on this rubber band, I stretch it, and I also know that the rubber band can push back and therefore come back to its original position. So this is a fairly good model of a rubber band, and once you can use it for certain applications, like you can store energy in a rubber band if you stretch it. So if you do that 1,000 times and put that around the watermelon, you can do this. But then what happens if I keep stretching this rubber band? If I stretch this rubber band beyond the limits of what my theory predicts, it will tear, and then my theory breaks because I have not accounted for the material properties of the rubber, the shear and the strain and all of that. And so what that tells me is that I now need to add more things to my theory. And in the same way, neutrinos tell us that this model is not complete, and that's very exciting because that tells us that neutrinos are pushing the limits of what our theory can predict. And by studying them, we can unlock the next paradigm that will tell us more about the universe. Now, why do neutrino astronomy? I will tell you in a little bit, but one reason to do neutrino astronomy is that nothing can really stretch limits like the cosmos. And so I'll give you a couple of examples. You have supernovae. This is the Crab Nebula. It exploded around 1054, recorded by Chinese astronomers. Back then, you can see it during the day. It was that bright. And now, you see all of this was a single point here, was a star. And what happens is stars, when they run out of fuel, they collapse on their own weight, and then sometimes they explode. And that's how most of the heavy elements are created in the universe. They also emit 99% of their energy in neutrinos. And we actually think that neutrinos may be causing the explosion. The pressure from the neutrinos, we think, causes the explosion. But we won't know that until we detect enough of these to verify this. By the way, this is a real picture from the Hubble Space Telescope. And so is, okay, so is this one. So this is a spiral galaxy. This is recorded by, again, the James Webb Telescope. And some galaxies, most galaxies have a black hole at the center, and some galaxies have a black hole that is active. And by active, we just mean that it is sucking up things around it. There are stars and material that's around that get sucked in, and there's a lot of activity happening near the black hole. And so this again stretches the limits of what we know, which is black holes sucking in matter and producing nuclear effects that we can see with neutrinos. Another very exciting prospect is neutron star mergers. Now, neutron stars, and I will show you. Oh, I'm going to stop using this thing. Okay, so neutron stars have the mass of the sun roughly, but it's concentrated in a radius of the size of Manhattan. So it's a very, very, very dense object. And sometimes there's two neutron stars that are near each other, and they get close enough that they start falling into each other. So this is a flying bird for comparison. So this is slowed down significantly. This happens very quickly. And most of the matter, as you're about to see, is going to merge. And then eventually a black hole is formed from the merger of these stars. And so a lot of neutrinos get emitted in this process as well. And by building a neutrino telescope and detecting high-energy neutrinos, we can measure some of the nuclear processes and the fundamental properties that cause these neutron star mergers. Okay, one last thing is our own sun. So we didn't really know what powered the sun until we confirmed it with the measurement of neutrinos in the 1960s. There was speculation and there was a lot of debate, but it was only confirmed when we were able to measure the neutrinos coming from the sun's core. So when fusion happens, again, nuclear process emits neutrinos, you can measure them on Earth, and this is what the sun actually looks like in neutrinos. So you can look at the sun's core by detecting the neutrinos that are coming out. Okay, so that's one reason you can stretch your understanding, and the universe gives you a great way to do that. There's lots of extreme events happening. But you can also see the universe with new eyes using neutrinos. So what do I mean by that? So this is the optical sky. This is what you would see with your naked eye if you were looking out at the galaxy. And you see the galactic center right here, but it's obscured. A lot of the activity is being obscured by gas clouds and dust. But if you look at the same galaxy in infrared, now we're looking at the heat coming out from, you can see the difference here. You can still see the center, but the galaxy is illuminated. Now, if you look at the same sky in gamma rays, these are much, much higher energies. Talking about a billion times higher energy than light that you can see with your own eyes. And now you start looking at what we call the high energy universe. These are processes that you could see, for example, that the things that are outside our galaxy start popping out. And it's not just our galaxy that's visible, although our galaxy is still very visible here. And these are active galaxies, again, that have a jet pointing in our direction. So they're very bright in gamma rays. But if you go further, the universe becomes opaque because light likes to interact, and the higher energy it is, the more it interacts. And at some point, it has so much energy that it will be absorbed before it has time to get to you. So you will not see the universe at these energies. So this is another way to illustrate it. So this is distance versus energy, and you see that at some point the universe is obscured at the highest energies and the largest distances, and it's only revealed by neutrinos, because neutrinos can travel without interacting reach Earth. So that's why we do astronomy with neutrinos. We do it because, first, they're electrically neutral, so they're not deflected by magnetic fields. They reach us directly from the source, just like photons. They have a very small mass, so they travel very near the speed of light. They can trace nuclear processes, which is important in understanding nuclear physics and also the universe. And they rarely interact, which means that you can really get at the core of extreme events, and because they're not absorbed, but also they're very difficult to detect for the same reason. So you need huge detectors usually to be able to see neutrinos coming from the sky. So the way we detect neutrinos is by looking at their byproducts. We can't see the neutrino itself. This is a nuclear reactor, and you see this bluish hue that's coming out constantly from this reactor. And that's because light is slowed down in media. So light has a constant speed in vacuum, but when it's traveling inside of a medium, light can feel electrons. So when it feels electrons, it slows it down a little bit. But when charged particles that are very energetic are traveling through the same medium, they can travel faster than light in that medium. And it's the same effect that you expect when you break the sound barrier. If you break the light barrier, you produce a cone. And I have this little animation. You produce this cone that tracks the particle going through the medium, and this is usually blue light. So you see a cone of blue light that emanates from the charged particle as it travels faster than light in the medium. So to detect that light, all you need to do is to go to a very, very dark place and build one of these things. So that's it. We have an example of that right over there. This is essentially a light bulb in reverse. So in the same way that electricity can give you light, light can give you electricity, and these detectors just sit there, they're passive, they wait for light to come in, knock off an electron, and then that electron is then captured, that charge is then sent up, and you record a charge which tells you that there was light that hit your detector. Oh. Okay, so this is the evolution of neutrino detectors as a function of time. And what you see here, we call this the Cherenkov effect, by the way, when blue light cones are emitted. And you see that at some point you reach what's called I think this is the cost limit. So at a certain point it just becomes cost prohibitive to build bigger and bigger and bigger detectors. But luckily, we can use natural sources, natural media, like water and ice, that are clear, and just instrument them. Put light detectors in water, put light detectors in ice, and just use the ice that's been given to us, the medium that's been given to us, with very little cost, and be able to build larger and larger detectors. So IceCube here sits right at the top at about 1 billion tons of ice. It's how much volume it instruments. This was not supposed to be in here, but this is a Super Kamiokande detector. So this is, as I was saying, that you're reaching the limits of what we can build ourselves. So this is a giant hole that's been dug into a mountain in Japan and filled with kilotons of water. So it's the same idea, it's just a man-made medium that they put pure water in and are able to detect neutrinos that way. The problem is that we need it to be about 10,000 times larger than this to be able to detect the neutrinos that we're after. So to do that, you can go to Antarctica. And in fact, what people discovered when they went to Antarctica and tried to measure the optical properties of the Antarctic ice was that at some point below 1,000 meters, light can travel somewhere between 100 to 300 meters without interacting a single time. So this is the clearest solid that's produced in nature as far as we know, or even in a lab. We cannot recreate this in a lab. So this is the effect of more than 50,000 years of pressure on on the Antarctic ice that causes this material to be as clear as it is. Okay, so now that we have our light detector, we have our medium. This is the IceCube Neutrino Observatory, and I'm going to walk you through a little bit how it was built. So this is the lab. It's just a few people go there every year to maintain it. There's a bunch of power supplies in here and computers that collect the data. But the detector itself, of course, is under the ice. And this is a schematic of what that looks like. Now that's that building I just showed you. So you just need to dig 86 holes, each 3 kilometers deep, and put about 6,000 of these detectors that I told you about. Okay, so to do that, you need to start off in Christchurch, New Zealand, which is the closest destination to the South Pole that you can get to just by commercial flight. And then from there, you wait for some time, sometimes days, sometimes weeks, for the weather to be just right so that you can hop on a military aircraft that takes you to McMurdo Station, which is at the edge of Antarctica. Of course, that is just the first leg. What we're getting to is here. So in order to do that, you wait for another few days or weeks, depending on weather, and then you get on another plane, this one a lot less comfortable. And then this is called Ivan the Terrabus, I think. You take Ivan the Terrabus as well. Okay, so once you're there, you need to dig the holes. And so I have this little animation of how these holes were dug. It's an ingenious idea. So first, you go through the first 50 meters or so, which is just very fluffy snow that you can dig through. And then what you do is you get a water hose, and you just push hot water out and let the hose fall on its own. So there's no digging required. You just have to make a lot of hot water and push it very quickly. And then you wait for about a day, I think it takes for it to fall all the way down. And so the nozzle here delivers about 200 gallons of water per minute. And in fact, the generators that were used to heat this water and push it out were, I think they're going to show up in just a second, they are car wash generators. So this is not very complicated. Yeah, so this is the operation. This is the hose. So this is what 3 kilometers of hose looks like. And then, yeah, these are the hot water generators. So it took about 6 to 8 years. I think it was construction started in 2002 and completed in 2010. You can only go to the South Pole during the South Pole summer, which is our winter. Because there are no flights in the winter. It's too dangerous. But there are a few people that stay there, and we pay them very well to stay there over the winter. Okay. So this is a picture that was taken actually from inside the ice. So you can kind of see these strings after they were put in. Now, once you put your strings in, you just have to connect a bunch of cables. So this is what people were doing. These are the cables that send the data up, and then you hook them up to some computers, and then you use a very old military satellite that they very graciously let us use to send the data from the South Pole up north. And this is what an IceCube event looks like. So I superimpose the Empire State Building for scale, and then I'll describe to you what's going on. So each point here is one of these modules I told you about. So red is early and blue is late. So this event was going from this direction to that direction. In fact, this was taken just a few months ago. So we send out every high energy event that we get, we send out an alert so that other telescopes can look in the same direction and see if they see something interesting. This event in particular was likely, so this is, the Earth is down below. So this is a neutrino that went through the Earth. And we know it's a neutrino because nothing else can do that. and it interacted very near the detector and produced a charged particle that traversed the length of the detector. So we see many of these. In fact, only 2 years after turning the detector on, we'd seen about 28 of these events. And these are the highest energy neutrinos that have been recorded to this day. And for that, we detected a flux of extremely high energy neutrinos coming from, I'll tell you in a second, coming from outside of our galaxy. So the IceCube experiment won the Breakthrough of the Year award in 2013 for science and experimental accomplishment of building IceCube for this discovery. Like I was mentioning earlier, these neutrinos come from outside the galaxy, and that was the first surprise, and it was a big surprise, because if you look at the universe and everything else, it shines very brightly in the galaxy. So our galaxy is the nearest thing to us. It should shine brighter. But what we see in neutrinos is that, so this is the galactic plane, and what we see is that the events are coming from everywhere. So these are events coming at us from much larger distances. Oh no. Okay. So I told you about active galaxies. We've actually detected one very recently. This is NGC 1068, and this is what it looks like in optical light, and this is what it looks like in infrared. So you see there's a lot of activity in the center. And what IceCube saw was about 80 neutrino events in 10 years of data collection coming from the direction. So this is the number of events as a function of the distance from the center of this galaxy. And you can see very clearly how, as you get closer and closer to the center, the number of events increases. So this is the first extragalactic neutrino source that we can confidently say has been detected. I told you that the galaxy is very dim, but there are very clever people working on the experiment. That it's not me, but it's someone decided to do an analysis with 10 years of IceCube data and use innovative techniques, and discovered that we can, in fact, see the galaxy. It's just dimmer than the extragalactic neutrino light, but you can see it. And so this is the first picture of our galaxy in neutrinos. And this came out, I think, just this past year. So now you can see it in optical, in gamma rays, and in neutrinos. This is not all of the science that IceCube does. IceCube can do many things. It can study the properties of neutrinos themselves. Apart from astrophysics, which I told you about, it can also study beyond the standard model. So looking at what the peculiar properties of the neutrino are and how you can introduce new things to your standard model to explain their properties. You can also look for connections with dark matter. And we also have a lot of glaciologists and just earth science people that are really interested in this detector because it's at the South Pole. And so we collaborate with people in the earth sciences as well. The IceCube collaboration is composed of several hundred people from many institutions around the world. And this is a picture from a recent collaboration meeting of IceCube. Not everyone goes, but this just shows you how much work goes into building such a thing and maintaining it. And then this is what our plans are. So we have an upgrade to IceCube coming that will make it even 10 times larger. So this is called IceCube Gen 2. And then, like I said, you can actually put these detectors in water. So there's one that's already being built. It's mostly done in the Mediterranean Sea. And then there's one off the Pacific coast of Canada called P1 that's also in the process of being built. And then there's one that's being built in one of the largest freshwater lakes in the world in Baikal in Russia. And so the combination of all of these experiments is supposed to give us much more exposure, and then combining the data from all of these experiments will help us understand much better what's going on, because as you saw here, the picture is still a little bit faint, and we need more data to understand in more detail what's happening. And so I will take any questions you have, and I'll leave you with this video that someone took in Antarctica one night of the Southern Lights. So thank you very much.
Any questions?
Right there.